Welcome to NPTEL online course on machine learning and deep learning, fundamentals and applications. In my last few classes, I explained the concept of the discriminant function, and also I explained how to take a classification decision with the help of the discriminant function. If I have the information of the class conditional density, then I can easily determine the discriminant function. That means if I have the information of the parametric form of the probability density function, I can determine the discriminant function. So in my one example, I considered normal distribution, that is the Gaussian distribution, and corresponding to this, I determine the discriminant function. Also, based on the covariance matrix, I have different discriminant functions. If the covariance matrix for all the classes are same, then I will be getting a linear discriminant function. On the other hand, if the covariance matrix for all the classes are not same, then I will be getting a quadratic discriminant function. Also, I explain how to determine the decision boundary between the classes for these cases. Case number 1 is if I consider the covariance matrix for all the classes are same, that is the case number 1. And another case I can consider the covariance matrix are not same for all the classes. So based on this, I can determine the decision boundary between the classes. So that means if I have the information of the parametric form of the probability density function, I can determine the discriminant function. So the parameters we can determine with the help of these two popular algorithms. One is the maximum likelihood estimation technique and another one is the Bayesian estimation technique. That is, the parametric form is known, but I have to determine the values of the parameters. So for this, I have to consider these popular techniques. One is the maximum likelihood estimation technique and another one is the Bayesian estimation technique. Suppose if I do not have the information of the parametric form of the probability density function, then also I can determine the discriminant function. If the classes are linearly separable, then with the help of the training samples of different classes, I can determine the discriminant function. So that concept I am going to explain today. So what is the concept? We do not have the information of the parametric form of the probability density function, that is the class conditional density. We do not have the information of the probability density function, that is the parametric form is not known. In this case, I can determine the discriminant function with the help of the information of the training samples of different classes, and we are assuming that the classes are linearly separable. So that concept I am going to explain today. So let me begin this class. So we are discussing now the linear discriminant function. Linear discriminant functions. So these classes are linearly separable, so that is why we are considering the linear discriminant function. So we don't have the information of class conditional density and the classes are linearly separable, and we can design a linear discriminant function. So the linear discriminant function, maybe I can write like this: Gx is the discriminant function, W is the weight vector, X is the input feature vector, and W naught is the bias. So this is the weight vector, and this X is the feature vector, and this W naught, and that is actually the bias, or maybe I can consider the threshold weight. This X is a d-dimensional feature vector. X is a d-dimensional feature vector. So this equation, this is a linear equation. If you see this equation, this is the equation of the discriminant function. So this is a linear equation. Now based on this discriminant function, I can take classification decision. So what are the decision I can take? So if gx, that is the discriminant function, is greater than 0, then corresponding to this, the vector x is assigned to the class omega 1. And suppose gx is less than 0, then the vector x is assigned to the second class. So we are considering a 2-class problem, and suppose the gx is equal to 0, and that is actually the decision boundary. So this is the equation of the decision boundary. So that means gx is equal to 0, the vector x can be assigned to either class. So and that is the concept of the discriminant function. Now we have to find the nature of the weight vector. So that means the problem is we have to find the nature of the weight vector w. So let us move to the next slide. So if I consider 2 points, so I can consider 2 points, suppose x1 and x2 on the decision boundary. So corresponding to these 2 points, what will be the equation? Because corresponding to the decision boundary, g1x is equal to g2x. So that means I can write corresponding to the decision boundary, wt x1 plus w naught is equal to w transpose x2 plus w naught. Since x1 and x2 lie on the decision boundary, so I can write like this. So this is the equation of the decision boundary. So that means from this equation I can write w transpose x1 minus x2 is equal to 0. So that is the equation of the decision boundary, and here you can see it is the inner product between w and x1 minus x2. So this vector x1 minus x2, this vector x1 minus x2 is a vector lying on the decision surface. So is a vector lying on the decision surface. This vector w is orthogonal to any vectors lying on the decision surface, since the inner product is 0. So this is actually the inner product. If you see, this is the inner product. The inner product is 0. So the meaning is vector w, that is the weight vector, is orthogonal to any vectors lying on the decision surface, since the inner product is 0 for 2 arbitrary vectors. Here we consider H is actually the hyperplane. H is the hyperplane. So that is the hyperplane between the classes. Now based on the discriminant function, how I can take a classification decision? So in my Bayesian decision theory already I have explained, but same thing I want to repeat this here. So move to the next slide. I can show you how you can take a classification decision based on the discriminant function, that is the linear discriminant function. So suppose we are considering x naught. So x naught is equal to 1 because we are considering this x naught is equal to 1, and suppose we have x1, x2, xd, so this is x1, suppose x2, xd, because we are considering the d-dimensional Fisher vector. So my Fisher vector is x is equal to x1, x2 up to xd So this is my feature vector. This is the feature vector x, and suppose I am considering this the final classification node. The final classification node is this, and corresponding to this I am getting the output. Output is gx. So how to determine gx? So the connection is like this. So it is connected to this, and weight is W0, that is the bias. Corresponding to this, it is connected here, and weight is W1. Corresponding to this, the weight is W2, and corresponding to this, the weight is WD. These are the weights. So it is a simple linear classifier having D input units and is corresponding to the value of the components of an input vector. So I am repeating this. So it is a simple linear classifier having D input units and is corresponding to the values of the component of an input vector, and each input feature value xi is multiplied by its corresponding weight wi. So that means the xi is multiplied with wi. So we have the output unit. So this is the output unit. Output unit. So what is the function of the output unit? The output unit sums all these products and emits a value. The value is +1 if W transpose x plus W naught is greater than 0. So what we are considering, W transpose x plus W naught, actually we are determining with the help of this connection. So output unit sums all these products and emits a value, the +1. So it will give the value 1 plus 1 if W transpose x plus W naught is greater than 0, or it will be -1 otherwise. So you can see that how to take a classification decision based on the discriminant function. The gx will be 1 if W transpose x plus W naught is greater than 0, otherwise it will be -1. So this is how actually we can determine the discriminant function. Now let us see what is the meaning of the gx. So what is actually the gx, the discriminant function? So it is actually the algebraic measure of x from H. So it is a algebraic measure of x. X is the feature vector from the hyperplane, from H. H is the hyperplane. So it is a algebraic measure of x from H. So actually what is the meaning of this? So let us explain this concept. So suppose we are considering one hyperplane. So this is a hyperplane we are considering, and we are considering a three-dimensional feature space. So suppose this is x1, x2 and x3. So we are considering the hyperplane. The hyperplane is H, and we are considering one arbitrary point here. Suppose the point is x. So this is the x is the point we are considering, and we are drawing a perpendicular to this plane. We are drawing a perpendicular to this plane, and foot of this perpendicular is suppose xp, that is the foot of the perpendicular, and this length of the perpendicular, and the length of this perpendicular is r, suppose. So the x, the point x is considered, and suppose it is the distance from the origin to the point x, and from the point x we are drawing a perpendicular to the hyperplane, and xp is the foot of the perpendicular on H, and we are considering the weight vector. So this is the weight vector that is perpendicular to the plane, hyperplane. So this is my weight vector that is perpendicular to the hyperplane, and one distance we are considering, the distance from the origin to the hyperplane. So the distance from the origin to the hyperplane. So suppose this is the distance of the hyperplane from the origin. So that is, we can determine W naught divided by W norm. So that is the distance from the origin to the hyperplane. So in this figure, again I am repeating, we are considering a three-dimensional feature space x1, x2, x3. Now in this case we are considering a hyperplane. The hyperplane is H. So this is the hyperplane is H, and we are considering a point X in the right side of the hyperplane, and you can see it is a distance from the origin to the X we have shown, and from the X we are drawing a perpendicular to the hyperplane. The length of this perpendicular is R, and what is XP? XP is the foot of the perpendicular on H. So what is the equation of this decision boundary? The equation of the decision boundary is Gx is equal to 0. So already I have mentioned. So that is the equation of the decision boundary. So this is the hyperplane, and the equation of the hyperplane is Gx is equal to 0. So here we are considering this. Now what is X? X I can represent like this. X is nothing but XP plus R W and W norm. So what is this actually, this value? Actually this is the unit vector perpendicular to H. This is the unit vector perpendicular to H. So that is the meaning of this. So corresponding to this, what is the Gx? Gx is nothing but W transpose X plus W naught. So we know this equation. So now I am just putting the value of X here, because X is nothing but XP plus R and the unit vector. So it is W transpose XP plus W naught plus R W transpose W and W norm. So just I am putting the value of X here. So if you see this part, W transpose XP plus W naught, this part if I see, this is actually 0, since the point XP lies on H. So now this Gx we can write like this: Gx is equal to R W norm. I can write like this. So from the previous equation I can write like this, because if you see here, this actually this W transpose W is nothing but W norm square. So if I put this value, then I will be getting Gx is equal to R W norm. From this, the meaning of Gx I can write, that is the meaning of Gx, the distance of X from H. So what is Gx? Distance of the vector X from the hyperplane from H, and scale by the weight vector, the norm of the weight vector. So that is the interpretation of the discriminant function. So if you see the interpretation of this equation, the interpretation is this: the distance of X from H and scale by W norm. So move to the next slide. So that means in my previous slide I have shown Gx is nothing but the distance R, and it is scaled by the norm of the weight vector. So that is the meaning of the discriminant function. So what is r? R is the distance. So gx divided by w norm. So that is the meaning of the r. And if I consider r is positive, suppose if the r is positive, that means if the r is positive, so what is the meaning of this? X lies in the positive side of the hyperplane. So that means the meaning is the x lies in the positive side of H and vice versa. So that is the meaning of R. So R we have determined, that is R is nothing but Gx divided by W norm. So this equation, it is very similar to the equation of a straight line. So if you see how actually it is similar, this equation of a straight line what is the equation of a straight line? So I can write ax plus by plus c is equal to 0. So this is the equation of a straight line. And suppose the distance of a point, suppose the point is x1 y1 to the line. So I want to find the distance of the point x1 y1 to the line. So line is represented by the equation ax plus by plus c is equal to 0. So what is the distance? So this distance is nothing but d is equal to a x1 plus by1 plus c root over a square plus b square. So it is a two-dimensional case. So if you see, this is very similar to this expression. So r is the distance of the point x from the hyperplane. And we have considered in the two-dimensional case, if I consider the two-dimensional case, the equation of the straight line is given by this. And if I consider the distance of the point x1 y1 to the line, that we can determine like this. So d is equal to a x1 plus b y1 plus c divided by root over a square plus b square. So this is very similar to the equation of r. So r is equal to gx divided by w norm. So what is the distance of the origin from the hyperplane? That already I have shown in the figure. So distance of origin from the hyperplane is h, is nothing but w naught divided by w norm. So this w naught is positive when the origin lies on the positive side of the hyperplane and vice versa. And if this w naught is equal to 0, that is the bias is equal to 0, that meaning is the hyperplane passes through the origin. The hyperplane passes through the origin. And in this case I will be getting gx is equal to just w transpose x. So I will be getting the expression for the discriminant function like this, if the bias w naught is equal to 0. So two expressions of the discriminant function in my next slide. So one is the linear discriminant function. Linear discriminant function gx. How to write the linear discriminant function gx? So that is nothing but w naught is the bias, and we are considering the d-dimensional feature vector. So wi xi. So this is the expression for the linear discriminant function, and I can give the expression for the quadratic discriminant function. So what is the expression for the quadratic discriminant function? Gx is equal to W naught plus I is equal to 1 to D, the D dimensional feature vector, plus we are considering the quadratic term, I is equal to 1 to D, J is equal to 1 to D, Wij, Xij, Xi, Xj. So you can see Wij is the interconnection between the nodes. The nodes already I have shown in my previous figure. So this is one equation for quadratic discriminant function. Now let us see how we can do the classification with the discriminant function. So I will be discussing two techniques. One is one versus all classification and another one is one versus one classification. So let us discuss about these two techniques of the classification with the help of the discriminant function. So first I am discussing about one versus all classification. One versus all classification. This is the first technique, and this is called OVA technique. One versus all, OVA. So for OVA, we are considering C discriminant function for a C class problem. So that means we are considering C discriminant function, C number of discriminant functions for C classes, C number of classes. So this ith discriminant function generate a decision boundary between the class I and the other classes C minus 1. So in this figure you can see, if I consider the class omega 1 versus all, I can consider the decision boundary 1. So this is the decision boundary 1. So in one side it is omega 1 and in another side it is not omega 1. That means other classes. So in one side it is omega 1 and another side is not omega 1. And similarly, if I consider this decision boundary number 2, decision boundary is 2. So one side is omega 2. So this is one side is omega 2. And the second side is, other side is not omega 2. That is with respect to omega 2 versus all. And similarly, if I consider omega 3, so corresponding to omega 3, suppose if I consider this is the decision boundary, 3 is the decision boundary. So in one side it is omega 3 and in another side it is not omega 3. And if I consider the decision boundary number 4, you can see, so in one side it is omega 4 and another side is not omega 4. That means I am comparing one class with all. That is why it is one versus all. So if I do this like this, then you can see we are having the ambiguous region. So this is the ambiguous region that is shown in the pink color. So what is the procedure? So the procedure is the ith discriminant function, ith discriminant function generates a decision boundary between class I and the rest of the classes, I and the other C minus 1 classes, that is the rest of the classes. The test sample is assigned to the class having the largest value of the decision function amongst all the C discriminant function. So based on this procedure, I can take a classification decision. That means a particular test sample can be assigned to the class having the largest value of the decision function amongst all the C discriminant function. Because we have C number of discriminant functions, we have to find the largest one. And corresponding to this, you can see I have the ambiguous region in the feature space. Now move to the second technique, that is one versus one classification. So move to the next slide. So the next technique is one versus one classification technique. One versus one classification technique. So this is called OVO. The previous technique was OVA. Now it is the OVO. So for a C class problem, in this case we have to consider, for C class problem, we have to consider C minus 1 divided by 2 number of discriminant functions. So we are considering, for C class problem, we are considering C into C minus 1 divided by 2 number of discriminant function. So discriminant function Cij, it is trained using the samples from the class I and j. So this is the discriminant function. It is trained by considering the samples from the classes I and j. That means containing positive and the negative samples. So it is trained by samples from class I and j. That means containing positive and negative samples respectively. So for I it is the positive sample, for j it is the negative samples. So whenever the decision function value for a test sample is positive from the discriminant function Cij, the vote for the class I is incremented by 1. So whenever the decision function value for a particular test sample is positive from the discriminant function Cij, the vote for class I is incremented by 1. Otherwise, the vote for the class j is increased by 1. The sample is assigned to the class with a maximum number of votes. So this is the procedure. So you can see here, this is the 1 versus 1. So we are considering the class omega 1 in the figure. So you can see another class is omega 2, and you can see the decision boundary between the classes omega 1 and omega 2. So number 1 is the decision boundary between the class omega 1 and omega 2. And number 2, if you see, if I consider this is the decision boundary number 2, that is the decision boundary between the classes omega 1 and omega 3. And number 2. And this number 3, that is the decision boundary between the classes omega 3 and omega 4. And this is number 4, that is the decision boundary between the class omega 2 and omega 4. That is, actually we are doing 1 versus 1 classification. And corresponding to this also, you can see I have the ambiguous region. But the area of the ambiguous region in this case is less than the OVA classification technique. So we have shown the decision boundary between the classes. So number 1 is the decision boundary between omega 1 and omega 2. Number 2 is the decision boundary between omega 1 and omega 3. Number 3 decision boundary is the decision boundary between omega 3 and omega 4. Number 4 decision boundary is the decision boundary between omega 2 and omega 4. So like this I have all the decision boundaries, and just you can see we are just taking the decision based on 1 versus 1 comparison. In both the cases you can see I have the ambiguous region. One is the 1 versus all, and this is 1 versus 1 classification. So how to avoid the problem of the ambiguous region? So let us move to the next slide. So how to avoid the problem of ambiguous regions. So to avoid this problem, we are considering C number of linear discriminant functions. For a C class problem, we are considering C linear discriminant functions. So we can assign the feature vector x to the class omega I, that assign the feature vector x to the class omega I if gix is greater than gjx for all I is not equal to j. So that means for C number of classes I have C number of discriminant function, and what is the classification rule? The classification rule is the feature vector x is assigned to the class omega I if gix is greater than gjx, and corresponding to this I can consider a linear classifier. So what is the linear machine? The linear machine I can consider like this: x is my input feature vector, and corresponding to this I am just determining the discriminant function g1, g2, all these discriminant function I can determine. GC, so C number of discriminant function, and out of this we have to select the maximum one. Which one is maximum? So this is a g1x, we have g1x, this is g2x, this is gcx, and which one is the maximum discriminant function we have to determine, and based on this we can take a classification decision. This is a linear machine. So for C number of classes I have C number of discriminant function, and with the help of this I can take a classification decision. So corresponding to this my decision boundaries may be something like this. So corresponding to this my decision boundaries may be something like this. So I have the classes. So this is the class omega 2, this is the class omega 1, this is the class omega 3. So this region is R2, this region is R1, and this region is R3. So you can see the decision boundary produced by the linear machine for a 3-class problem. This is the decision boundary I can have corresponding to the linear machine. Also I can consider this type of decision boundary. Suppose this is my class omega 3 and the region is R3. So this may be omega 1, corresponding region is R1. This is omega 5 and corresponding region is 5. This is region 2 R2, and suppose the class is omega 2. This is the class omega 4 and corresponding region is R4. So you can see in the first case we have considered the decision boundary for a 3-class problem. So in the first case I have shown the decision boundary for a 3-class problem. So this is a 3-class problem, 3 classes. The second one is a decision boundary for a 5-class problem, 5 classes. So you can see the decision boundary between the classes. So one is omega 1, one is omega 2, one is omega 3, omega 4, omega 5. So you can see these are the decision boundaries. So with the help of the linear and discriminant function I can do the classification. In this class, I have explained the concept of the discriminant function, and also I have explained the physical and the geometrical interpretation of the discriminant function. After this, I discussed the concept of the one versus all and one versus one classification techniques. The problem is the presence of the ambiguous region. So, to consider this issue, I am considering C number of discriminant functions for C number of classes, and I have to pick the largest or the maximum discriminant function, and based on this I can take a classification decision. In my next class, I will be explaining the concept of determining the discriminant function with the help of the training. So, that concept I will be explaining in my next class. So, let me stop here today. Thank you.